This podcast was produced by OAR FM Dunedin with support from New Zealand On Air.
The Science Notes podcast on OAR FM Dunedin, brought to you by the Division of Sciences at the University of Otago. I'm Dave McMorrin. Over the next half hour, I'll be chatting with a graduate science student about their research, their passion for science, and the things that fuel their creativity. Well, hello there and welcome again to another episode of Science Notes. My name's Dave McMorrin and this time our guest is Alex Haack. Hi Alex.
Hello.
Alex is doing a PhD in chemistry.
Yes,
at Otago University. And in fact he lives in an office not very far from mine. So he was convenient to wrangle into doing this show today. So thanks for coming along and telling us a bit about what you're up to. Before we get into the nuts and bolts of it, though, tell us a bit about your background. How is it that you find yourself doing a PhD now in Dunedin, on the other side of the world to where I think you started off?
well, that is true, yeah. So I am from Germany. I was born there.
Whereabouts?
In Braunschweig, which is pretty central, actually, a bit to the north. And back there I did my bachelor's in material sciences and then actually another bachelor in geology in Göttingen, which is also a city nearby. Then I did a master's in crystallography in Freiburg in the very south. And then I found a PhD position that would get me to New Zealand, though it's a cooperation between a Helmholtz Institute in Germany, in Hamburg. So actually what I did, I started the first 1.5 years in Germany at that Helmholtz Institute. And then like February last year, I came here and now I'm in Dunedin.
So was that always the intention for the PhD, that it would involve being here?
Yes, definitely. Yeah.
And that was an attraction?
Well, to be honest, of course it was. Like I wanted to be in another country, preferably an English-speaking country, because, you know, English is everywhere and you need it, especially as a scientist. But actually after I finished school, I already been to New Zealand for 7 months doing like a classical work and travel, as lots of German students did. So actually I knew New Zealand already, which, you know, so of course being in another country, very interesting, but New Zealand was pretty much the second best country that I knew of because I was here 7 months already. But of course I knew it was a very nice country. I'd like to be here again.
And had you been to Dunedin as part of that?
Actually, no. Like I think I stopped here one night just for another tour to the Catlins, through the Catlins.
Oh, you did well going to the Catlins at least, rather than just here on the way to Queenstown or something boring.
Well, I've also been to Queenstown, all these kind of things. But like Dunedin wasn't a big stop, or like there was nothing special as a tourist, I think, for Dunedin.
Yeah.
At least for me, like there's a steeper street and all these kind of things, but I missed that. Yep. But now I've been here again. Actually, I missed the Moriaki boulders. So that time I wanted to be there, but it just couldn't fit in. So, but now I've been there like 3 times because I really like them.
Yeah. Because you're a geologist in part.
True.
Yeah. So, interestingly then, so your geology background then, along with your chemistry background and your crystallography background, I suppose all kind of tie into what it is that you're studying now, because you're interested in making use of minerals in New Zealand.
Yeah. So I started off as a geologist, but then I thought, you know, like lots of that is paleontology and like these long timescale things, which I wasn't too interested. Like it's interesting to learn about it, but it didn't really feel like science.
Yeah.
Like proper science. That's why I switched to material sciences, was more about crystallography and petrology and these kinds of things.
Yeah. So this is more about the structure of the minerals and how the composition is related to the properties of them.
And why atoms sort out these crystal structures and all these kind of things, which is just very interesting.
Yeah.
So then I got a little bit away from geology, doing my master's and all these kinds of things. And then I found this PhD, which was, you know, back to my geology roots, which again is very interesting. Yeah.
So the work that you're doing is, as you said, it's part of, it's to do with the Helmholtz Institute for Hydrogen Technology. So what sorts of technologies to do with hydrogen is the Institute involved in, and then how does your PhD fit into that?
So what that institute is especially doing is hydrogen storage.
Right.
Because like energy storage in general is always a problem. And hydrogen especially because, you know, it's a very volatile small gas. It corrodes everything. And so like storing hydrogen is actually a problem. And what that institute is specialized in is the storage in metal hydrides. So we don't store the hydrogen gas as a gas because then it's very reactive.
Yeah.
But we store it as a metal hydride. So we chemically bind it into the metal. And then it's just like every other chemical compound with some hydrogen in there. But with metals, or with especially iron titanium, the metal that we are thinking about using, we can do it reversibly. So we can absorb and desorb at different temperatures, different pressures,
Right.
and that's making it like a hydrogen storage material.
Yeah. Yeah. So I think we've talked about this actually on the show with other guests. There's these sort of sponge type compounds,
Exactly.
these metal organic frameworks, which are a way you can just sort of trap the hydrogen in the pores of it, much like you trap water in a sponge. But you're doing a slightly different thing. You're
Yes,
doing
like
chemistry to kind of attach the hydrogen, but then you can undo the chemistry to take it out again.
Yeah, so in a MOF, in a metal organic framework, they are like holes where the hydrogen as a molecule fits in, but we are like splitting the hydrogen in two separate hydrogen atoms, and then it's just chemically bound within the metal. So it's just a solid metal block. We use it as powder to have more surface area and all these kind of things.
So the hydrogen's on the surface rather than inside it, the way it is for these other spongy type things.
No, it's also like within the bulk metal, within like there's like iron atom, hydrogen atom, titanium atom, hydrogen atom.
Okay, right.
So it's like throughout the whole metal.
Okay,
Yeah.
right, cool. So why iron titanium for you?
Like hydrogen storage metals, there are some more like magnesium and like some other containing lithium or alanates and all these kind of things. Iron titanium is very interesting for two reasons. For one, it's a room temperature hydrogen storage material. So as I said, like the threshold for between absorbing hydrogen and desorbing hydrogen is around 40 degrees, which is roughly room temperature. And others are working at 300 degrees and all these kinds of temperatures, and also different pressures, which are just not very usable for like everyday tasks.
Yeah, I mean, if the whole point is to try and do it with the least amount of maximizing the energy.
It's just about
to drive your car
or
or whatever. If you're spending half the energy just doing the absorption and desorption, you're kind of
exactly,
it's not so good. Yeah.
And then the other thing, iron and titanium are very abundant materials, so one could really upscale that to like steel industry. We have lots of iron.
Yep.
So both of them are potentially usable to have like lots of that material. Titanium in this case is the biggest problem. Titanium is actually quite expensive, but that's just because the titanium oxygen bond is very tough, so it's hard to break that.
Yeah.
But we need the titanium metal.
Yeah.
But that's exactly what my PhD is about, and trying to produce that iron titanium somewhat cheaper, so that especially in this case the titanium part gets like not so expensive, and that of course makes the whole system expensive.
Because if you have iron and titanium and oxygen, then it doesn't bind the hydrogen.
Not at all, no.
No. So that's unhelpful.
True, yeah.
So then you're looking then at taking these naturally occurring iron, titanium, oxygen rocks, in effect, and trying to find an experimental way of taking the oxygen out.
Exactly, yeah. So that's why the other part is in New Zealand, because here on the South Island on the west coast, there's lots of ilmenite. Just the black sands that we know, that's basically ilmenite, and ilmenite is iron titanium oxide.
Right.
But as you said, as long as the oxygen is in there, we cannot use it as hydrogen storage material. So I, simply have to remove the oxygen, and then I end up with iron titanium, which is exactly the phase that we need for hydrogen storage.
And from a chemical point of view, that seems straightforward.
Exactly, yeah. Just an easy reaction equation.
Yep.
But as I said, especially the titanium oxygen bond is very strong. So, we need lots of effort to get rid of that oxygen. So what I use is different reducing agents, because, we know that there are other elements that bond oxygen even stronger, and then in theory the oxygen should jump from the titanium to, in this case, either magnesium, calcium, or calcium. So these are the two that I used. So what I do is mix the ilmenite just from the beach. Pretty much, we are not allowed to use the sand from the beaches itself. That's not allowed, but the land behind that.
Yep.
And we're allowed to use that ilmenite. So I have that sand. I mix it with, and like now I focus mostly on magnesium, and then put them in a ball mill, for example. So I have like a jar with lots of steel balls, and then I have this sand of ilmenite and magnesium powder in there, and then like the balls, with the rotations and everything, these balls have mechanical impacts between the vial wall and the steel balls and the powders in between, and these impacts are enough energy to induce this reduction reaction. And then the oxygen jumps from the ilmenite to the magnesium, forming magnesium oxide. And I end up with a mix of ideally iron titanium metal and magnesium oxide. But then I just have to separate those two phases, which is actually rather straightforward. And then I end up with hydrogen storage material.
So this ball milling, this process, which I find fascinating, and I've dabbled with a little bit in the past. You don't have to, I mean, if people think of like a chemical reaction, you think about sort of glassware and bubbling solvents and Bunsen burners and all this sort of stuff. None of that for ball milling. There's no solvents. All you're doing is putting in your ilmenite and putting in powdered magnesium, which itself probably isn't the easiest thing to use. Is it pyrophoric?
Everything I do, I have to do in an argon glove box.
Oh, no, of course, you've got this big glove box. Yes, yes. So everything's under no oxygen anywhere. Because I suppose you're trying to get rid of the oxygen. You don't want to have oxygen there. So there's that, yes.
Plus, like if the iron titanium metal would also oxidize over time. Yeah. And then like the oxygen would fit into the iron titanium interstitial spaces. And then it's not hydrogen storage anymore.
Yep.
So that's why all I do is like in a specific argon atmosphere. So there's no oxygen around.
So these big boxes with the windows and the big gloves and stuff.
Yep. I use them every day.
Yep. And so you just grind them up and you have like little ball bearings.
Exactly,
and you just so have you got a spinning one? I'm waving my hands here, sorry, it's the radio, I know. But a spinning one or a shaky one or
a spinning one?
A spinning one.
A planetary ball mill,
Right, yeah.
So there are lots of impacts, and like because I'm not allowed to use any oxygen, I cannot use water or like ethanol or these kind of things because they all have some oxygen in there, and then put oxygen into the system again. So that's why lots of things I do is just dry, and like it's just about the physical impacts. So it's like physical chemistry. So I'm not putting reagents together and like having a red solution turning it green or something like that. It's just the physical impacts.
Yeah, I know. At its simplest form, you can actually just use like a mortar and pestle. I mean, you can't, but you can do chemical reactions this way. You just grind them up.
It's the same idea.
And the thing happens, So that's presumably, what sort of scale do you do this on?
Right now I use around 5 grams of powder.
Okay, so that's quite a lot.
Yeah.
But in terms of scaling this, assuming you magically work out how to get this working really well, obviously you'd have to do it on a larger scale than that.
Well, there are like very big ball mills in industry, so they use it for, actually I don't know exactly, but they are like, right now my ball mill is like, 10 centimeters in diameter, like they are like, I'm not meter, probably not, but like they are very big ball mills around. So it does work, scaling up there.
I remember there used to be a cement works in Burnside, just up over the hill from Dunedin here, and we would go through it when I was like in primary school, and they would have the way to take the raw cement and then grind it into a powder was that it had effectively the same thing. Yeah. Only the balls were like 20 centimeters across, and the container they were in was the size of a normal house.
Oh, wow.
It made quite the noise.
Okay.
But but to do it on that sort of scale, but you'd still have to do it under argon. Yeah. You'd have to keep the oxygen away.
Yeah, of course.
So that would be a thing if you're going to scale it up, but it's doable.
I hope so, yeah.
Yeah.
I guess so.
One of the things you said in your notes is that it's not quite as simple as just taking the oxygen out, because what you want to have left behind is a compound where you have a 1-to-1 ratio of the iron and the titanium.
Yeah, so again, like with a simple equation, we just get rid of the oxygen. But what I found, and what you probably could have known before, is, of course, it's not that straightforward. There are also other things going on in the ball mill. And so what I end up with is like 40% of iron titanium, which with a nice 1-to-1 ratio between iron and titanium, which is exactly what I want. But the other 60% are iron titanium in a 1-to-2 ratio, so twice the amount of iron in there. And that is not hydrogen active. So I need to get rid of this phase. And that is also accompanied by like probably it's like some titanium, like pure titanium amorphous phase, which I cannot measure with XRD, where these numbers are coming from. So I need to alter my ball milling process a little bit so that like less of this 1-to-2 phase is being formed and more of the 1-to-1 phase. So I need to find out why this amorphous titanium phase is formed, so I can try to not produce it.
Right, and so that then leads to hundreds of different fiddling with the conditions.
Exactly, yeah. Like there's like I can change the speed the mill is running. I can just change the time, how long I run it. I can add other things into the ball mill, like hexane or something, which does not have any oxygen inside, and try to see if that, changes the thermodynamics or whatever exactly it is. Probably just the energy that I transfer to the powder. I try to modify all these parameters so that, I do change the ratio between the 1-to-1 and the 1-to-2 iron titanium.
And you said that, so you do the ball milling and you come up with a powder, and then you have to analyse that. And there's various different ways that you've mentioned in your notes that you go about doing that. Can you talk us through a little bit about how you go about working out the ratio of the FETI to the Fe2Ti and stuff?
So the simplest thing is just the XRD, so X-ray diffraction, because that can differentiate between different crystallography phases.
Right. So this is back to your masters.
Yeah, pretty much.
Crystallography stuff. Yep.
Yeah. So XRD is a very basic tool, quite quick. And then I see like the nice iron titanium peaks, which aren't like always the same positions, and the nice iron 2 titanium peaks. And then I can differentiate and also calculate exactly these numbers, 40% to 60%.
Right. And you do that in the department?
Yep.
With the X-ray that's on the ground floor?
Exactly, yeah.
Right.
Which is actually quite interesting, but that's a single crystal machine, which is different from a powder machine. And I think I'm the only one using powders, so we have to do little tricks to get the powder work in a single crystal machine. Yeah,
we did a wee bit of that back in the day as well, but it was always, yes, it's not quite as good as having a dedicated machine, but it's there, so. Yeah.
And it works, and that's fine. And the other thing I use is SEM, so scanning electron microscopy.
Right.
Where we then pretty much have a powder, we put it in resin, then we polish it, so we have cross sections of the different powder particles, and then we scan it with electrons, and that gives us very nice pictures, and then we can see the morphology, and like in the best case can differentiate between different phases, like the iron titanium, the iron 2 titanium.
So they at that scale they look different.
Well, the scale actually is a problem because I'm milling it, and with milling I pretty much mix everything I make it as small as possible, and that's actually smaller than actually what we can the resolution have of the SEM. So that actually is a problem that I cannot really distinguish those two phases. I can distinguish pure iron that is in there, and there's also like some garnet and quartz in there, just because it's a natural raw material that I use.
Yeah.
So I can see those things, but actually the iron titanium and iron 2 titanium, because they are quite similar, I don't really see a difference in the SEM. But I can also do EDX in the SEM, so measure the the energy of the X-rays that come from shooting electrons onto the sample.
Right.
And with this energy, I also can differentiate which elements are inside different particles that I measure, and then I know there's more iron in here, there's less titanium in there, and then can try to paint a picture from that.
Right. Cool. Yeah. And then the other thing that you mentioned, which I thought was interesting, is this Bayesian optimization algorithm stuff.
So it's something I just recently started a couple of weeks ago, because someone I met in Germany in the Helmholtz-Zentrum, who actually now works in Canterbury, he's like a theoretical chemist, so like doing lots of calculations. And like in one of our 2 monthly meetings, he just said that there are these like Bayesian optimization algorithms, which I never heard of, because I'm an experimentalist. But I always found it quite interesting what these guys can do just using a computer. And then we kept talking, and then I wrote a Python script using like a already existing Bayesian optimization algorithm. So I like, for me, that's just a black box that does something. I have to write a Python code to get my data and feed it and get the data out.
To be fair, I looked up what these were. And the AI answer said, this is a black box method for working out stuff.
That's how it works nowadays. I don't know.
Yeah.
But that's quite cool because I did all my experiments, and like as I said, I figure out which parameters work best to get the highest yield of iron titanium. But with all the parameters I can change. That's like a huge parameter space where I could do like an extreme amount of experiments and trying to figure out which is the best. Yeah. But of course, altogether, one like an AI, or like in this case, this algorithm, can predict certain things with a certain certainty. And that's why I can feed this algorithm all the results from my experiments and all the input data, like milling time, milling rotation, process control agents, whatever I used. And then this algorithm can predict, okay, with what we have right now, it seems like this set of parameters will give you the best or highest iron titanium yield. And that, makes my life a bit easier. So, so that there's like an algorithm who can calculate all that. And then I can just give that a try, whatever that algorithm tells me. And then of course, I can double check, is the reality what he predicts? Yep. What the algorithm predicts, and then,
feed that back in and on you go. Yep. So how long does a typical experiment take?
I have a standard procedure, so that's like this is the standard procedure, and then I just change little things from that to see which direction do we go from here. And that's an 80-hour run at 350 RPM in this case.
80.
Yes.
Okay, so you can't be doing thousands of these.
Yeah,
because you've only got three.
I always have one working over the weekend, so it feels like I do something and it just runs over the weekend. Yeah.
Cool. So you've found that it takes that sort of 3 or 4 days to.
Like I tried 1 hour, 24 hours, 40 hours, and if I 24 hours definitely does not work. So that's just not enough impacts. That the reaction from the oxygen from the ilmenite to the magnesium is at least fully done.
Yeah.
So I need at least 24 hours. I know that. I tried 40 hours, but then again, everything looks a bit not 100%, and that's why right now I'm working at 80 hours and keep that as a standard.
Yeah. Cool. Well, so you're about halfway through, right?
A bit over that, yeah.
A bit over that. Plans for after the PhD? I mean, obviously, hydrogen technology stuff is not going away. There's lots to still do. Are you planning on staying in the game? Or?
Always more to do. Yeah, I think so, because now I do have some expertise, at least in hydrogen storage. So I think it makes sense for me to stay here, and I like it. Of course, the biggest question would be if I stay in New Zealand or go back to Germany. There are good reasons to do both. I'll probably apply for more industry jobs than academia, just because it seems more money and. And not just 3 years contracts and all these kind of problems that academia has.
Yep. Is there options for staying in industry in New Zealand in this area?
I definitely know some startups that use hydrogen for energy transfer of whatever. So there definitely are at least some startups that I know of. I'm definitely thinking about applying for them. Yeah. And of course in Germany there are even more options and research institutes that always do hydrogen work, and especially the EU is investing lots of money into hydrogen.
Are there actually sort of in actually on the ground systems using hydrogen for running vehicles or whatever in Europe in a way that there isn't here yet?
No, I think that's more like a philosophical question, or what who knows what the future will bring. And hydrogen has lots of problems, and definitely the first thing lots of people forget is if you can use electricity directly, that's always the best option. It doesn't make sense to first transfer it to hydrogen and then the hydrogen back to electricity. You lose so much things on the way. So always go electricity first, and that's why probably the cars, at least from what I heard in the hydrogen community, will stay with batteries because it's just more efficient. Because a car is something you use pretty much every day, and if you use it for every day a week, then directly using electricity is best. The hydrogen come into play when we want to store energy for long terms, from summer with lots of solar energy to the winter times. That's when hydrogen is being used. Or every time you have lots of energy, but you cannot use the electricity as it is, so you want to store it somehow, and then hydrogen would just be these extras that we overproduce. Yeah.
Sure. Okay. So there's lots to do.
Definitely.
But thank you for telling us about what you've been up to at this point.
Thank you for having me.
And thank you everyone out there for listening. We will finish with a piece of music that Alex has brought in, and that is...
Cassiopeia by Il Civetto. German band, Italian name. They also sing French.
All right. Thanks for listening, everyone. You've been listening to the Science Notes podcast, brought to you by the Division of Sciences at the University of Otago. To listen again, or to find other episodes in this series, go to Otago Access Radio's website, oar.org.nz, or to your favourite podcast platform.
This podcast was produced by OAR FM Dunedin with support from New Zealand On the Air.